Great, excellent. Well, hello everybody. Great to meet you. I'm Daniel, founder of Nexus, and this is Jens, our chief scientist. So I'm just gonna give a little bit of the intro and the outro, and Jens is gonna take it over like the middle part of the presentation. So very briefly, we're a company that works on advancing verifiable computation. And what we say is that just how OpenAI develops intelligent compute models, we develop verifiable compute models. And these verifiable compute models are general purpose verifiable compute models. So you can prove anything that you want. We call this zero knowledge virtual machines. And the zero knowledge virtual machines, they just get faster and faster and faster in each iteration. So we just recently released like CKVM3, which was about 1,000 times faster than CKVM2. That was about 100 times faster than CKVM1. Which was about 10x faster than CKVM0, which was actually presented here at Stanford in September of 2023. And these machines essentially allow you to prove whether a program has executed correctly or not. And so the topic today is just on the research and the interesting part of the intersection between artificial intelligence and verifiable computation. And we take an approach that is very practical. We think about verifiable computation not only from the research perspective, but from the product perspective as well. And so what we care about is how do we actually prove the correct execution of AI models? Not only theoretically, but as a software product that you can essentially throw something like a shallow neural network inside a general purpose zero-knowledge virtual machine that emulates a system such as RISC-V, the popular instruction set architecture, and just get something proven, right? And so, very briefly, why would we be interested in this? So, in all honesty, we're just interested in it because we think it's intellectually interesting. We're still trying to find, a few many reasons, but there are some that are like at high level discussed. For example, can we prove that we're running the right AI model? Because if I give you an answer that claims that this is from model 03 or something like that, I can't really prove to you if it actually came from 03 or from DeepSeek R1 or something like that. So can we prove that it came from the right model? Can we prove that the model behaved correctly? Can we prove that the model operated over the right set of data? And the compliance is, part of like privacy, for example, or like there was a time where I was taking a flight with a founder that was working on an AI robotics company, and he was telling me, Daniel, I want to be able to show that if my robot, killed somebody because of an improper inference, that I can say it was not because of me, the company, it was because I was running the right model from Google, and the model from Google predicted whatever, right? And so, this gets very deep into law and all of that, and that's why we're excited about it. So, at a very abstract level is, when you run an AI model, you're running an algorithm that produces an output, given an input. Our CKVM and verifiable computing models do this, and in addition, it gives you a proof, a very succinct proof of computation, which is just a few bytes. And so the question is, how can we get it done with an AI model and not a generic program? Is this the next slide?
It is.
Oh, great. So once again, our CKVM is a system that operates over general purpose programs. So you can literally just almost copy and paste your favorite Go program, your favorite ROS program, and just put it on the CKVM and it generates a proof for you. But AI models are pretty complex and they consume a lot of computation, whether that's for training, obviously, and inference as well. And we can't take the naive path to achieve this. So we can't just like emulate matrix multiplications or vector matrix products or something like that and just run it on the CKVM. We actually need to be smarter than that. And the question is, how can we build a working prototype that is usable? and that is able to achieve something as basic as the inference of a very shallow, very basic neural network. And it happens that it's not easy. Well, I'll leave it to Jens to explain what we're how we do it.
Thanks. Yeah. Okay. So I guess one point I want to make is that so far, I mean, there's been some really great research and some great prototype built for verifying AI, but they sort of like assume that you have sort of like a very clean model. They're fairly small models, so they sort of like set up themselves for success, right? And I think in the real world, we have like such a diverse world of AI, right? So there's a ton of different use cases, and if you look closely, you can probably see that also this slide is AI generated. And if you look underneath, right, then there's also a diversity of the models that people are using and the kind of inference systems we have, right? So the question is, okay, how can we prepare our CKVM, right, such that it can handle all of those different types of AI? And also handle sort of like the rapid changes that are happening in the AI field, right? That one model, will be what we're using today, and then tomorrow will be a different type of model and different type of computation that we need to verify. So the advantage of a CKVM, which is something we're building, which is something that many other teams are building as well, so it's a broad field, right, is that we are really aiming at general purpose computation. You can take any type of program and stick it into it. So people are looking at lots of different types of instruction set architectures. We're looking at RISC-V, which is something which is well established, has a lot of tooling already. Okay, and if you think about a VM very abstractly, what does it do, right? It takes an input. Maybe some of the input is explicit and maybe some of it is confidential, right? And it produces some output. What a CKVM adds to that is a proof. So you get both a result, but you also get a proof that this result is actually correct. Okay, and corresponding to that, there's a verification algorithm that will check the proof, right? And the explicit inputs, but not the confidential data, right? And then they would check that, is this actually correctly computed or not? Okay, so one important realization that has happened in the field of verifiable computation is that verification can be really cheap, much cheaper than the computation you're doing, right? So this proof here is really small. We're talking about like even if it's like a really complex protocol that's running for a long time on lots of data, the proof may be in the order of hundreds of bytes. Okay, and correspondingly, the verification time is also really small. So of course you have to read the explicit data that you are verifying something about, but that's really the limit of the cost of verification, right? So the proof is small, you do a small computation on that, we're talking about milliseconds or something like that, and you are verifying this enormous computation, right? So even if you're running like, these kind of like multi-billion-dollar training runs and you wanted to verify the whole computation of that, it would be extremely cheap to verify. Okay, one cool thing in addition to that, right, you can imagine if the proof is so small, right, then it cannot possibly hold much information and leak information, right? And we actually have this zero knowledge property, which is sort of like where the CKVM comes from, right? Which says that you're not actually leaking any information, right? So of course the output of the computation may reveal some information about the confidential data, but except from that, the proof does not reveal anything. Okay, so what is the status today? Okay, so verification, the proofs are really small. Okay, the computation when you are verifying something costs almost nothing. It's really cheap to verify. Okay, there's no such a thing as a free lunch, though. The cost of proving is enormous. Okay, so we're paying several orders of magnitude, right? So again, if you wanted to do a $1 billion training run, right, and now you want to do that verifiably, so you want to prove that you have done that correctly, now we're talking trillions of dollars. Okay, and of course we need to do better than that. So we are seeing these rapid improvements in performance of the CKVM. So that's going to be much better next year. And there's also sometimes some opportunities to take shortcuts and do something more clever than just like proving directly the recomputation. So I'm putting this timeline here just to illustrate like the improvements we've seen in the ZK space. Right? So back in the day when these proof systems were first invented in the 80s, right, then people didn't even consider the time that it took to prove something. They just said, like, if I have a proof and it has infinite time, then it can construct a proof. Right? And then we've seen sort of like a movement across more and more complex domains. So in the early days, it was sort of like identification schemes, which were really tied to cryptographic operations. So it was sort of like, we're using a tool that's sort of like related to the tool that we want to prove something about, right? And nowadays, we're seeing sort of more complex kind of operations. So in the blockchain space, maybe you want to verify that a smart contract has been executed correctly, right? So now we're talking about arbitrary code and computation and so forth, okay? And we're not there yet with AI, but I think we will get there. And my hope is that, in the next years, we will see that now AI also falls into the space of what is feasible to prove. Okay, so I want to illustrate this question, right? Because I talked about how expensive it is to prove. So I want to illustrate then sometimes you can do something more clever. So there's a very recent paper, which I think is neat. Okay, it studies convex optimization problems. So what you have there is a loss function that tells you how good is the model that we're looking at. Okay, and it's a convex function, right? Which means that you can say there's some uniquely defined optimal model, right, where you minimize the loss. Okay, it may be that you cannot, like, with bounded training time and bounded precision, actually achieve exactly that optimum, okay? But the idea then is, let's not try to recompute the training run and prove that every step of that training run is correct, right? Let's instead just look at the model and check, is that a good model? Is it close to that optimum, right? And the paper then defines essentially a notion of like closeness, like how far are we from the optimal, how close are we to it, and prove then that, we are epsilon close and we can get there in reasonable time and we can have a model that is close to that. So that's one example of a way that you can sort of like be smart about proving a model is good. And there are some advantages as well from a security perspective of this, right? So one thing you can do with a training run is you can also like, you can try a few times, you may get different models out of it, and you choose the one that sort of like fits your purposes. And you can sort of like do, it seems, less cheating when you're just looking at, is the model good or not, and have a measure for that. Okay. Another common operation is matrix multiplication. So lots of machine learning use matrix multiplication. We know that that is a costly operation to compute, right? So in the best case, we can do it with something like n to the 2.37 something operations. That's if you have a very idealized model, and in reality, it will typically be larger than that. But there's actually a really neat algorithm called Freivalds algorithm that allows us to check much more efficiently whether a matrix product is actually correctly computed, okay? And the idea is very simple. I'll take a pseudo-random vector, multiply that on the matrices, and test whether these two, the left-hand side and right-hand side, are identical, right? Of course, if A times B is equal to C, then you're just computing exactly the same matrix vector product on both sides. If they're different, however, then with a high likelihood over this choice of the pseudo-random vector, we're going to catch the cheater. Okay, so that means that we can verify cheaper than we're actually computing.
Should I talk about this one?
Yeah, let's give that to you.
Yeah, so I want to talk about this a little bit more concretely, and it's because we actually have, a medium-sized engineering team, well-sized research team, and how we actually go about implementing some of these like special purpose instructions that we see in AI models and other such systems. And it is actually in a very straightforward way, which is we have a machine that has some instructions. It's actually around 42 RISC-V instructions. And in order to accelerate special purpose computations, such as matrix multiplications or tensor products or ECDSA signatures or something like that, we just extend the number of instructions in the machine and implement what you can consider ASICs, so circuits that just extend the machine. We call this precompiles, right? And these have been central to the architecture of the verifiable machine that we've built pretty much since day one. The tricky part here is that executing a given instruction, like the cost of executing that given instruction should only be proportional to the cost of proving that given instruction. And so those of you that may be familiar with building chips, you may recall that a chip may have special purpose accelerators for hashes, for example. So SHA-256, even ECDSA signatures and other such primitives. So the CKVM, a verifiable machine, has similar, extensions that allow us to massively accelerate the performance of these systems. And in particular, the CKVM that we just released has the ability to be extended with custom precompiles by third parties. And so part of our research efforts with some of our partners in the industry is researching, documenting, and developing these extra instructions for computations of interest. In the special case of AI, these include activation functions, so nonlinear functions such as ReLU, sigmoids, etc. And in the case, like the most important operation is that of matrix multiplication or tensor products, right? So multi-dimensional tensor being, multiplied together. But it's actually not easy. It's not easy because these operations operate over floating point or floating points, right? And how do you prove, number one, the correct operation of multiplication with floating points with the given precision target? Number two, how do you, can we go back? How do you prove, something like matrix operations using something like Freeveld's algorithm or something like that? And then how do you encode it in a precompile? How do you document it? How do you benchmark it, et cetera, et cetera? But the good thing is that we have a repeatable process for building these special purpose instructions, shipping them, and allowing developers to utilize them just by importing a library. And but this requires a good amount of research. So part of what the work of our research team is applying some of the techniques that Jens was just describing, such as rethinking what soundness and correctness mean for some of these computations. So in the particular case of floating point operations, a question is like, hey, do we actually want to prove that whatever floating point operation is exactly precise, or are we fine with saying that the result is within some epsilon amount of what we want to do? Because if that is the case, then the way in which we design this custom extensions and the provers actually varies. And that's kind of the things that we do in collaboration with our partners, but it's also that developers don't actually have to even think about it, right? You as a developer just import whatever library that accelerates whatever functions you want, and that's it. Something that we are planning pretty soon is, because all of this works over Rust, and as you know, AI developers don't really use Rust that much, is can we integrate this in a very easy way with PyTorch and TensorFlow, for example? can we make it so that the whole verification process is invisible, so that when you're building your AI pipeline and all of that, you just add the CKVM sort of like as an intermediate module to get the proof that you want. We think that this has just not been achieved. There are a few projects that have been building this, but a little bit of the end game of verifiable AI, it's a little bit far away, but there's a huge amount to be discussed around developer experience. And all of what is being discussed today is just like, the challenges with theory and engineering, which are pretty hard. But how do you make it so seamless that you as a developer don't even have to think that you're utilizing all this technology and you're just getting like a proof done? The future is, as it pertains to this area, is you have two AI models that are talking to each other. Maybe they distrust each other. Maybe, they don't really like each other, right? Oh, we're on time? All right. Well, hopefully they like each other. But the goal is for them to share proofs. And this has actually been deployed in real life, some of this. We actually have proven shallow evaluations of neural networks. And so you can read all about it in our blog post. But thank you, everybody.